event. Daniel's going to talk about neural network application. And he's probably going to answer all our questions about that, right, Daniel?
Yeah.
Well, hello, everybody. My name is Daniel. I work here at the Southwest Research Institute. SWRI is kind of a special place for a lot of reasons. One in particular is that our business model sort of tends to create these very interesting portmanteaus of capability. The section that I work in particular has two sort of in-house things that we focus on. On the one hand, I have like these world-class flight software engineers who, quite literally put Cygnus into space, which means that they did the most important part, the flight software. On the other side, we have myself and some colleagues of mine who really focus on machine learning, engineering, analytics, this sort of thing. Not historically for space, but for a lot of other tangential business areas. So, for example, oil and gas, utilities monitoring, that sort of thing. What I found, though, in talking to people on both sides of the aisle, is that the data problems are kind of the same. Fundamentally, what we'd like to do is make use of all this data we're collecting from all this instrumentation out there for decision making, right? Either whether it's autonomously controlling something or trying to figure out which information we should beam down from a spacecraft or from an IoT device out in the field. It's the same kind of problems. We have all this data and these very, very narrow pipes to get the data back through. This is particularly interesting in space because we're seeing this newer and newer generations of instrumentation coming online, both on ground and up there in space, that are capable of these just massive, massive volumes of data. The LSST is the one that everyone here on the ground is just panicking about right now. It's going to be coming online in the 20s, 20 terabytes per day, just a monstrous amount of data. And the processing tools currently are not in place to handle that data volume. So we're going to be getting all this information telling us about the cosmos, but it's useless to us unless we can very nimbly, very agilely process that data, put it towards some use. Same thing in space. We have these instruments. This is Mass Specs. I'll be talking more about this in a minute. That are capable of just huge, huge volumes of data, in this case, respective to space links, that we cannot possibly downlink everything that might be of interest. Which brings us to the topic of today's discussion, is that my team and I have been working on a couple different AI-based solutions to mitigate this problem. In this case, what we'd like to do is put a machine learning AI algorithm onto a spacecraft so that it can automatically select which portions of a data stream from an instrument such as Mass Specs are relevant to a science mission, which is a scary proposition, especially if there's any space scientists in the room. I'm sure you're frowning right now. But it's a very interesting use case because it turns out for a lot of instruments, including this one, a lot of the data that's produced is just noise. So there's a lot of redundancy, a lot of waste in the data stream. So if you get some intelligence out there on the edge to do some of that processing for you, you could significantly return the science on your investment, right? This might or might not be interesting. I'm sure everyone has a working familiarity with machine learning these days. The type that I'm going to be talking about today is what's called a convolutional neural network. It's a type of deep learning, which is a type of machine learning, which is a type of data analytics. Data analytics is nothing new. Neither is machine learning, neither is deep learning. What's new is that in very recent years, the hardware, particularly on the ground, has matured to such a point that we can take very, very large neural networks and put them to use where we couldn't before because the densities just weren't there computationally. For our application, we were targeting a spaceflight FPGA because it's the best we got in space for parallel processing. On the ground, GPUs dominate the deep learning scene for good reason because in a convolutional neural network in particular, you're running lots of multiplication adds, basically in parallel over a very large input data. And in space, the closest to that in terms of capability is an FPGA because you can instantiate lots of parallel computations, right? There are some spaceflight GPU investigations ongoing right now. NVIDIA actually has I think a Titan X on the space station right now, and some other groups here and there are looking into flying GPUs as well. But right now, there's not a radiation-hardened solution on the market, and there probably won't be for a little while longer. So the challenges associated with taking a deep neural network to space are really the same challenges that are associated with taking a deep neural network anywhere out on the edge. You have this big, bulky, amazing network that has all these different nodes, millions and millions of computational nodes, that you're trying to fit on a very hardware-constrained device. And the trick is trying to, well, get it to fit and still do its job. Because what typically happens in the development process of these neural networks is that you start with something huge, so something that's way bigger than you could ever fit onto a hardware component that you actually want to deploy it onto. And you kind of start scaling it back a little bit to fit your device. Space, especially space-flight FPGAs, represent kind of an extreme case of that because space-flight hardware is just not quite as dense as, again, ground-based GPUs. Even the newer, like sleeker GPUs that you find on like these NVIDIA SoCs. Just a little bit more background about this particular data problem. This is a mass spec instrument. It's an instrument that we have developed here at Swery, so we had a lot of access to ground truth data for it, which is very important for these kinds of tasks. That's an example of the data over there. Here's really the main problem, again, reiterated, is that we just don't have good access to the same kind of massively parallel processing power that we do on Earth in space. The one exception to that might be as we start to see these clusters, I guess like these constellations, computing clusters come up in space where people's strategy is just to launch many, many, many satellites that all kind of share the computational paradigm. That's maybe a shift that could affect us, but I don't think we're going to have like a cluster, around Jupiter anytime soon. More data set description. This is just a couple of examples of what we're trying to do. So this is a time-of-flight mass spectrometer reading. You've probably seen a lot of this before. On the x-axis, you have a time of flight. On the y-axis, you have the basic intensity of it. And we're basically just going in there, trying to figure out where's there a real species, where's there not. So something a scientist could do easily here on the ground, may not so easily for like the lowest in our cases, but pretty trivially. Really, the whole goal is to put that scientist on the spacecraft out there around Jupiter. This is the model architecture we used. It's a one-dimensional convolutional neural network for anyone who's familiar with kind of CNN architectures. So the way this works for everyone else is that you have like an input signal here on the left. So it's a 1D array, so one big long string of numbers. In this case, it's a time-of-flight array. It goes through a series of multiplicative layers. So there's a whole filter bank of filters that all multiply by that input. And there's another filter bank that multiplies by that, and so on and so forth. And there's a whole bunch of fancy stuff in between that I won't go into right now. But on the output, if all goes well, you should get a segmented array of values with the exact same shape as the input size, but it'll tell you for every input if it's relevant or not. So in this case, it'd be a one-to-one input-output size where each portion of the output tells you for that input peak, is it a peak we want to take or is it a peak we want to reject, right? So a couple of things we tried out to make it fit onto a spaceflight FPGA were some kind of state-of-the-art techniques from network compression, which is a subfield of neural network study. This is kind of interesting. The gentleman who was speaking time before last, Michael, I believe, talked about a little bit of code coverage, particularly for neural network technology. There's a little bit of an overlap here. One of the domains of network compression is actually this idea of network pruning. If you imagine a neural network as you have your input, you have your output, there's many different pathways from the input to the output, maybe millions or billions. Not every single output is going to be exercised. In fact, most of them are not exercised in a lot of neural network applications. So one of the more interesting results of network pruning, which is the idea of figuring out which of those pathways is and is not executed, so that you can just get rid of it and it doesn't affect your performance but so much, is that you're also getting rid of a source of uncertainty for your network. I'm not in any way claiming that we have VMV'd our network. We've definitely not, but that's another interesting area that just got me thinking when I was watching another gentleman's presentation a moment ago. So the whole goal of network compression, these other techniques we're applying, was to just minimize the hardware footprint. That's in two ways, right? So the neural network is this big architecture of physically placed components on the FPGA hardware, combined with these, like a bunch of memory, really, for the weights that go onto the neural network, right? So we're really trying to minimize both of these, how much hardware it takes up, how much memory it takes up. Another approach that we applied was the introduction of sorry, I thought I heard something. Another approach that we applied was this introduction of the FIRE module. It's a fairly new implementation of convolutional neural networks that have been on the scene about a year or two now. Still too technical, I realize, but the idea is that someone figured out for a convolutional layer, you can approximate its functionality with half the weights. It's cool for a neural network geeks. I'll glaze over it, get to the good part. The results of our effort was that with all these improvements we made, we were able to get our size of the neural network so that its memory footprint over there on the far right of the table from 1.5 megabytes down to 236 kilobytes. And that is because of the number of parameters, so the nodes in the network was reduced by about threefold there. This is the sort of simplistic compression strategy we came up with. Just for some context for the numbers I'll show in a second. The size of the final packet, or the data field packet anyway, for transmitting this time of flight signal would be equal to 2 bytes just for the length of the packet field, plus the number of peaks, plus 2 times the number of peaks. So this is what it would look like in action, had it been running. On the top, you have your raw signal. On the middle there, in the signal classification row, you have a segmented output. So that would be like the raw output of the neural network saying, yep, this peak is good, that peak's good, that peak's not good. And on the bottom would be the final data packet. So in this case, we got 10-to-1 compression for this particular signal, which is actually pretty typical of the test set that we had given to us. So what's next for this area of research? There's a couple things. So one is there's an interesting, I guess, downside to neural networks is that, which is actually their benefit as well. They do really, really well on data that you give them to learn. So theoretically, a neural network can actually learn an approximation of any function you throw at it. So with enough capacity, enough size, that sort of thing, it can do anything you want it to do. However, they're really, really good at what you give them and not transferring to new things. So if you put this neural network out there in the field and you want to, say, safeguard against, what if there's a brand new thing that we didn't have in our training set here on Earth, which you would expect from like a science mission. You need a different topology perhaps than this type of network for that use case. So it'd be interesting to experiment with other network topologies in the area of anomaly detection, finding new stuff that you never encountered before to see if we could head off that use case, right? Or that pitfall. We're also interested in exploring higher dimensional data sets. So this was a 1D data set, but neural network technology expands to many, many areas, images, video, time series segments of things. There's many topologies that do many different things that we also would be interested in characterizing how well or how poorly the network parameters scale with network capacity and size and task. And then we could do further tests. I guess circling back to the point I brought in from Michael's presentation, we have thought about quite a bit, haven't got a whole lot of chance to do it yet, this idea of how do you validate a neural network? How do you actually sufficiently exercise it? All its different, billions of potential routes you can take through this network to determine, yes, it is safe for this or that application. Well, that was the end. Thank you so much.
Thank you.
Hi. First of all, very interesting presentation. And I was wondering if you guys had compared using a compression like this to using an interpolation. So where you'd have like a minimum threshold to turn on the interpolation and say, well, now we have this given signal, let's interpolate it using one of the many schemes available, and determining whether that was more friendly in terms of data size compared to like a neural net or another of the other techniques that are mentioned here. Thanks.
So when you say interpolation, do you mean like a lossy compression on the peak itself is what you'd be doing?
Yeah,
so
correct.
That was one of the interesting parts about this, that what we were trying to do was avoid touching the raw data itself. So we wanted to get rid of what is deemed noise, which has its own inherent risks. However, the peaks that we did preserve, we wanted to preserve the entirety of the data in its original format, which is why it was so important for the network to perform well on selecting those peaks, because that's where it gets the most bang for its buck, is guaranteeing, 90–95% of your peaks come through, that you can squeeze more in, right? Yeah.
Have you tried to augment your testing and development with what's called adversarial training? That is to say, there's ways to take a neural network and do things like change 2 or 3 pixels in a picture and make it completely wrong.
Right. Now for this project, we have done work in adversarial learning, especially for the automated vehicles. So that's a huge area of research. There's these guys just over there in that building that they have this sticker. It's about the size of a sheet of paper they can slap on the side of a double-wide trailer and make it look like a motorcycle to a neural network. It's crazy. It's really trippy.
There's some scary examples out there.
Oh, it's terrifying, yeah.
Goddard hosted an AI workshop last week, and actually there's a lot of good presentations. I just want to make you aware, I don't know if you're aware, DARPA is doing an explainable AI project. If you are, I can point to some information, because the goal of that was to make it more explainable to why it reasoned, to make that data available is why it came to the conclusion it did,
Yep.
so you could evaluate it.
No, yeah, thank you. We're fascinated in the area of explainable AI. I'm really excited to see what results come out of that, because right now it seems like it's more of a notion, explainable AI. There's been some, work here and there in it, but it's a very early area of research right now. And for good reason, it's very hard. Yeah.
Have you done any research or thought about if the CNN here is resilient to a single bit flip? And if you were to investigate that, you might be able to put it into a GPU, that something would be more resilient in space.
Right. We have not. No, that'd be very interesting. So in this case, you're talking about bit flips in the code itself, or the weights or something. Right. Yeah. We haven't done that analysis yet. Good point, though. Thank you.
All right. Daniel, thank you very much for the presentation.
Yeah. Thank you.